We're going to show you how to properly analyze a surface map by hand. This is a critical skill for all weather forecasters, particularly severe weather forecasters, as it helps to uncover the locations of surface lows, frontal boundaries, etc., all of which are important ingredients in many severe weather setups. While most upper air data that you come across will be already analyzed by the time you see it, that's not the case with surface maps. So performing a surface analysis by hand should be a frequent part of your storm chase forecasting and targeting. I'm going to complete a full surface analysis by hand of this map you see here. And as we go through, I'm going to be commenting on my thought process, giving you some tips and tricks, etc. Before we dive in, though, I do want to bring to your attention some things that you must remember when you are doing a surface analysis. So what a surface analysis involves is making contours of pressure, which, as we know, are called isobars. These are colored in black, and they're placed every 2 millibars. This lets you see small-scale fluctuations that you might not see with a larger interval. Every 4 millibars is acceptable if you're using a map with a larger domain, but if you're zoomed in on a specific region, using a 2 millibar interval is best. Now, the spacing between each isobar matters greatly because this tells us how strong the pressure gradient is, and because the strength of the pressure gradient modulates the strength of the wind, we need to really focus on getting our isobar spacing right. When isobars are tightly packed together, that means the pressure gradient is stronger, and therefore the surface winds are stronger. And when isobars are farther apart from each other, that means a weaker pressure gradient and weaker winds. So be sure that you're doing that interpolation properly. So if you have 2 points, one with 998 millibars and one with 1002 millibars as the pressure value, you want to make sure your 1000 millibar isobar goes as close to halfway between those 2 points as possible because, of course, 1000 millibars is exactly halfway between 998 and 1002. In the end, it's not going to be perfect, but try to keep it as consistent as possible. Also, make sure that your isobars follow the direction of the winds. In reality, things like friction keep this from being the case, but for our purposes when doing surface analysis, we always want to make sure our isobars follow the direction of the wind. As we're completing our surface analysis here in just a bit, I'll walk you through this in a little bit better detail. And also, we can do a little bit of smoothing when we're doing our surface analysis. We don't want our isobars to be really craggy and really wiggly and windy. It's okay to do some smoothing, but we want to make sure that we're following the direction of the wind as closely as possible, as that's going to be key for where to place our frontal zones, as some of those tiny fluctuations in the isobars based on the wind direction are going to be critical when placing our frontal zones. We'll get to that toward the end of the video.
The Chaser Academy is the best deal in storm chasing. Click the join button below this video and find out why.
So with that, let's go ahead and get started here. Some people like to start from the outer edges and work inward, and other people, myself included, like to start and try to find kind of the center of any circulation and kind of work from there outward toward the edges. So, as we get started here, right off the bat, you can see that we have kind of this little area of kind of spin right in here, and you'll notice our lowest pressure you can find is right in here at this particular station, 978. As we know from our second video in this series, that's a surface pressure of 997.8 millibars. It's written in code there. Again, if you want a refresher on what each of these values mean on these particular station plots, go ahead and flip back to video number 2 in this series. I like to start and try to find the center of circulation. Again, some people do it a little bit differently, but as long as the end product comes out the same, you know you've done it right. And as long as you find a way that's comfortable for you, that gets you to the right end product, you'll be doing a surface analysis correctly. So I like to start and try to find the center of circulation. Again, we've identified that kind of in here. Our lowest pressure is right here at 997.8 millibars. We're going to draw our first isobar at, let's say, 998. As for the interval between the isobars, the standard is usually doing isobars every 4 millibars, but it kind of depends on the domain that you're looking at. If you're looking at a much broader area, perhaps a map of the entire United States, you might do isobars every 4 millibars. But if you're doing a smaller area like this, I like to do them every 2 millibars just because that those small scale features really tend to pop when you do isobars at a little bit finer resolution. So for this analysis, we're going to do isobars every 2 millibars. So as we said, the lowest pressure within kind of this broad area of circulation here is this station right here, 997.8. And you'll notice every other station surrounding it, this one 998.3, 1000.3, 998.7, all these stations surrounding this one have a pressure greater than 998. So our first isobar is going to be the 998 millibar isobar. And it's going to be a closed isobar surrounding this particular station here. So I'm going to start right in here, 997.8 and 998.3. So we're going to go just about halfway between the two, of course, following the winds, northeasterly wind here. We go down a little bit, 997.8, 1000.3. So we're going to go much closer to the 997.8 station. 997.8, 998.7, same thing there. We're going to go up and around, and that is going to be our 998 millibar isobar. And of course, we're going to be labeling these isobars as we go. That's a cardinal rule of isopleth analysis. We have to label our isopleths in order to avoid confusion for the rest of the analysis. Now let's move on to our 1000 millibar isobar. We're going to start up in here. You'll see this station, 998.3. You'll notice a few of these stations up in here don't have pressure values associated with them for some reason. But we do have enough readings here to kind of give us an educated guess at where the 1000 millibar isobar is going to go. 998.3, 1004.3, 1003.8. So our 1000 millibar isobar is going to be much closer to this particular station here. I'm going to put it kind of somewhere right in here as a best guess. Of course, following the winds, more east-northeasterly or easterly winds up in here. But you'll see the wind change here to more northwesterly, so we're going to have to dip the isobar down a little bit to follow those winds. 1000.3, 998 isobar there, so it's going to go pretty close to this particular station. We're going to have to bring it down, though, and notice the more westerly winds here, so we're going to have to really kink it like this. And here's where it gets a little bit interesting. Notice here we have 998.7 and 1004.3, but down here is 1001.6. So in order to kind of do this, we're going to have to go closer to this particular station, and we're going to have to really go down and get closer to this 1001.6 station, something like that, roughly speaking. Now we have a 999.8 here, so we're going to have to kind of go over and up very close to that particular station. Then we have to go back through as we have 1000.6 up in here. So it'll be something like this, 998.7, 1000.6, so something like that. And you see the winds change back to more easterly up in here, 1001.6, 998. So we're going to go kind of over here, and that is going to be our 1000 millibar isobar right in there. Of course, remembering to label it as we go. So very interesting there. We have kind of a little bit of a kink in there. We're going to talk about that a little bit later. That'll help us place our fronts nicely. So let's go to our 1002 millibar isobar here. We have our 1000 millibar isobar here, 1004.3, 1003.8. So it's going to be kind of somewhere in here. Notice the winds up here are more northerly, so we're going to have to really kink that isobar down like that. And this is 1002, so 1000, 1005.2. It'll be a little bit closer to the 1000 one. Here we have 1000.3, 1003.4. And once again, we're going to have to really kind of go like that, noticing that those winds are more westerly out in here across northeast Kansas. 1000, 1004.3, same thing. And once again, we're going to have to kind of drop that like we did with the 1000 millibar isobar because of our wind shift here. And our pressures are a little bit less down here than they are in surrounding areas. 1001.6, 1004.3, 1002.6. So it's going to have to come through here. And so we're going to do that by kind of kinking it back like this, and then coming back up to follow the winds that are out of the southwest here at these couple of stations. So we're going to come back up, 1003.6, so kind of going in the middle of those, back up, and then we have one that's 1000.2 kind of out in here. So we're going to have to go bring this isobar a little bit farther out and then kink it back in, noticing the winds are more easterly up in here across northern Missouri. So we bring that up in there. Again, bring that isobar a little bit farther out, close to that 1002.2, and then to follow our winds, we're going to have to kink it back like that in order to follow the winds. 1001.6 up in here, so we're going to go just north of that and kink it back, noticing that the winds are more out of the east up here as well. And then we're going to finish the isobar. There's our 1002 millibar isobar. We'll label it at a couple of points here. And then move on to our 1004. So I see 1004.3. Here's our 1002 line. We'll start kind of right in here as well, 1003.8. So we're going to have to start up in here just north of that station right there, kind of going in between, following the winds as we said. 1004 going to be closer to that 1005.2 line. Again, following the winds more out of the northwest there. 1005.9, going to bring it back like this. 1004.3, so we're going to have to go just on the east side of that station right there. And once again, you'll see we have a 1004 station down here, 1003.8 right here, 1002.6. So we're going to have to once again make that kind of kink to allow for that us to go right through that station with this particular isobar here. So we're going to have to go down and get kind of right through that station, and then kind of back up, 1003.6, 1003.9. So we're going to have to bring it a little bit farther out here, kind of close to that 1003.9. A couple of 1004 plus stations right in here, following those winds. Now notice we have a 1004.1 station out in here, so we're going to have to once again go out a little bit with this. Following the winds, we kink it back toward the north, following that southerly wind right there. 1003.8, so we'll go on the north side of that station just barely. 1004 station right in here, so we continue to have to go up and then go over to follow those winds that are more out of the east or east-northeast right in there. 1005.4 will go just under that one. 1003.4 up in here, so we've got to kink it back up between that one and 1005. We'll go through there, and then we can kind of complete our isobar. So there's our 1004 millibar isobar. We'll label this one at a couple of different points, one over here as well, just to kind of avoid confusion as we continue to go through the analysis. On to 1006. I'm going to start up here once again, 1004.6, 1007.4. I'm going to go right through the middle of those, closer to that 1004.6, or actually right in the middle of those two. Following those winds, we go down here, and you see we have a 1005.2, 1007, so we're going to have to go out a little bit here. Once again, trying to follow those winds, bringing this one back due to the northwesterly flow right there. This one is 1006, so we may have to go a little bit farther out actually before we bring it back in. There, 1006, 1005.9 right in there, so we're going to have to go out and just on the west of that particular station here. Once again, as we said, not going to perfectly be parallel to these wind directions at every one of these stations, but that is a result of a little bit of smoothing here on our part. 1005.7, 1006.7, so we're going to have to go through here. And then once again, you see the winds shift a little bit. We have a 1005.1 or 4 down here, I can't tell. Nonetheless, we're going to have to kink it like our previous isobars in here, and we're going to have to bring that back up as well. 1006.6, we're going to go back up following the wind direction. 1005.6, we're going to have to go over as well to this station right here, 1006.2. We go back up following those winds. Same thing in here, split the difference between there and there. 1004.1, you don't see 1006 out in here, but I think it's safe to assume that these are going to be much higher pressure out here. So I'm actually going to bring this out and kind of do this out here. We have 1004.1, 1008.3, so we can kind of split the difference between those two and kind of curve it back due to those more easterly winds here. 1006.7, we have 1006.1 there. So in a perfect world, you may have to kind of kink this one back a little bit there and kind of go like this underneath, and we have to go up in here, 1004, 1007 up there, and then we'll kind of go around and kind of finish our analysis just under this 1006.2, and then we'll go up and around, and there is our 1006 isobar right there. So of course we label it couple different places here. Let's move on to 1008. Now I'm going to start up in here as well. So you'll notice that we have 1007.8, 1007.6, 1010.5 up here, 1008.3. So it's going to go something like this here. We're going to bring that down. We have a 1006.6 station right here. I'm not sure how much I believe that. And you'll come across this as you're doing an analysis. You might come across some data that looks a little bit wonky. We're going to come over to a station over here that looks a little bit wonky in a second. But I'm thinking that's a little bit off as far as pressure goes. So I'm going to ignore that for the time being. You can see the stations around it are much higher than 1006.6. So I'm not 100% sure that is accurate. So I'm just going to ignore that for this particular analysis. And it's okay to ignore stations that look a little bit wonky. But you have to make sure they don't really match with the stations surrounding it. And that doesn't seem to be 100% accurate to me. So 1008, we have 1007.5, 1007.5. So we're going to have to go kind of back out in here. You can see that the isobar spacing is getting a little bit wider here. Our pressure gradient's a little bit weaker out in here than it is closer to the surface low here. So let's go back down. 1008 once again. We're going to go through 1008.1, 1007.4. We'll go down in here as well. And we have 1008.5 and 1007.6. So we're going to have to bring this back out. And you'll notice that we don't have any more data here that we can definitively say, oh, we can bring this around, kind of connect it. So we're going to have to, what we have to do in that case is just kind of end it at the edge of the data field. And then we just kind of label it there, 1008. That's going to be the edge. We don't have enough data to be able to do anything else with this, so we just kind of end it off right there. Now let's go over here. Back to the bottom right corner, you can see that we can pick our 1008 line back up, 1007.0, 1009.2. So I'm going to start at the edge of the domain once again. And we're going to go back up and do the same thing that we have been doing this whole time. So we're going to split the difference here, 1006.8, 1008.2. We're going to go up like that. 1008 on the dot right here, so we'll go right through that particular station. And we'll go back out, 1006 line right here, 1008.4. And the same thing applies here. We don't have enough data here to determine whether or not we should continue this 1008 line. So what I'm going to do is I'm going to just kind of end it off right in here, and we'll do the same thing right there and label our 1008 line on the edge of the domain. Now we can pick things up right back in here, 1008.3. I'm just going to do that right in there, labeling our line as we have said. And then we're going to go back up 1007.6, so we're going to have to go up a little bit here and then go back through 1006.1. We have to go all the way back out in here, going up a little bit more. And then we've come to this station here. You see the pressure reading is 995.9, and that is completely erroneous. You can see all the stations around it are much, much higher, 12 to 18 millibars higher at all these surrounding stations. So this pressure reading is for sure erroneous. So we're going to scratch that out and exclude it from our data analysis. So we continue our line there after we've excluded that point. 1006, 1008.4, tight pressure gradient here. We're going to have to go right under that 1008.4 station, go back up, and then we'll kind of go around and close off the line. And there is our 1008 isobar. And I'm just going to kind of label it here at a few different points, and then we will move on to our 1010. We're almost done with our analysis, just a couple more isobars here. I'm going to start up in here. You see that we have our 1008, 1010.5 here. So I'm going to start things kind of right in here, very tight gradient up in there. And so we go back up, 1010.5, we go around here, kind of following the wind direction. And we have 1010.5, 1009.5, and a couple stations sub 1010 out here. So we're going to go back out and kind of do something like this. Again, not going to be a perfect analysis here. And you'll see 1009.9. Don't have enough definitive evidence to really be able to continue it here. So what I'm going to do is just kind of end it at the edge of the data right there, 1010 line right there, and we can pick it back up. You can see all these stations sub 1010 out here, so we don't have to worry about that. On that side of the map, we do have to worry about that out here, 1009.2, 1011.5, so we'll start our 1010 line here and just kind of do the exact same thing as we continue on. 1009.8 right there, and we don't have enough to continue it, so there we'll just end it off at the edge of the data field and label it, and we'll go up to the top right portion of the map. We do have enough. We'll kind of start it about right in there, I'll say. 1010 line goes underneath those couple stations. And we're continuing 1009.7. We'll go just above that, and then we will connect our ISO bar right there. And then, of course, we label it where we can. And that is our 1010. 1012, we can do that down here at the bottom. Just a little bit of a line there, starting at the edge of the data field, going up like that, 1012. And then we can do that up here as well, 1012, something like this. And then we just kind of end it off at the edge of the domain. All right, so we've completed our Isobar analysis. Now it's time to place our surface low and frontal zones. This is a diagram of a typical mid-latitude cyclone or low pressure system. These are going to consist of a surface low and a cold front and warm front that stretch outward from the center of circulation. You want to start out by placing your surface low, and that's going to go at the center of the lowest closed isobar you were able to contour. So on our surface map here, that is going to be this 998 millibar contour. So we're going to put in the red L, indicative of a surface low, right there. So you can see it's at the center of low pressure, where the lowest pressures are located, and at the center of circulation. The winds are rotating in a counterclockwise fashion around the surface low. Now, not every surface map you analyze is going to have a surface low. If you don't have any closed contours, then you're not going to be able to place any surface lows. And they're not always going to be as obvious as the one we've done in this example, where you have several closed contours and a clear location that the surface low is supposed to go. Sometimes they can be very subtle, so always keep that in mind. Let's now talk about placing our fronts. This is a diagram of a typical mid-latitude cyclone or low pressure system. In general, a low pressure system is always going to have a cold front and a warm front associated with it. Now, as a mid-latitude cyclone heads toward dissipation, the cold front will catch up to the warm front, displacing all the warm air off the surface, in which case we'd have an occluded front to go along with the cold and warm fronts. But overall, in a typical mature mid-latitude cyclone, you're going to have a cold front and a warm front. And these fronts are going to be connected to the surface low. You can't just have a cold front or a warm front out in the middle of nowhere without any connection to a surface low. Now, every low pressure system is different, but in most cases, the cold front's going to be draped down somewhere to the south of the surface low, while the warm front will be draped off somewhere to the east of the surface low. In other words, the cold front is always going to be trailing the warm front. If you imagine an eastward or northeastward movement of this entire system, the cold front's always going to be behind or trailing the warm front. Now, there are a number of things that you want to look for when you're trying to properly place a surface front. The first of these is a pressure tongue. A pressure tongue is a series of kinks in the isobars that extend from a surface low and are consistent over a fairly long distance from the surface low. In our diagram here, take a look at the cold front. Notice how all of the isobars kind of kink downward where that frontal zone is placed. That is a pressure tongue, and it's a telltale sign that you have a front in that location. Same thing applies to the warm front here. Notice the kinks in the isobars where the warm front is located. And a front is typically going to go right through where the pressure tongue is located. You also want to look out for wind shifts, changes in wind direction. For example, notice here that winds to the west of the cold front are out of the northwest, while winds to the east of the cold front are much more out of the southwest. Same thing with the warm front. Winds on the warm side are out of the southwest, shifting to much more southeasterly winds on the north or cool side of the warm front. These two are going to be your most reliable clues about where to place a frontal zone. The vast majority of fronts are going to include some sort of pressure tongue and wind shift. It may be fairly subtle, but in most cases, the location of a frontal zone is often associated with a wind shift and pressure tongue. These next two factors are not quite as reliable, but you do want to still look for them as clues to where to place a front. You want to look for temperature gradients, shifts in the temperature across the frontal boundary. For instance, on the cold side of a cold front, you might see surface temperatures in the 40s and 50s, shifting to the 70s and 80s on the warm side of the cold front. Also, moisture gradients, changes in the dew point across the frontal zone can be a good clue. You may see drier air on the cool side of a frontal zone compared to more moist air on the warm side. Now, not all frontal zones are going to be associated with a notable temperature or moisture gradient, but many of them are, and therefore you do want to be looking out for these when trying to place a front. And the critical thing to remember is that you want to see multiple of these factors in the location of a potential front to have confidence in placing that frontal zone. If you can only identify one of these 4 factors in the location of a potential front, that may not be enough for you to confidently place the frontal zone accurately. So you want to check multiple of these off the list when you're trying to place a front. You want to see a pressure tongue in the same location as a wind shift and temperature gradient, for example. That gives you fairly high confidence that a front is in that location, whereas if you only see a subtle temperature gradient without any of the other factors, that's likely not enough for you to be able to place that front accurately. So always be sure that several of these factors are present when you're placing a front. All right, let's go back to the surface analysis we did just earlier and try to put in our frontal zones. We'll start off with the cold front, and right away I see a pretty well-defined pressure tongue. Notice the kinks in the isobars there extending to the south and southwest of the surface low center. That's a good start. Definitely suggests that we may have a front there. Now let's look for a wind shift. And you can see we have a pretty clear wind shift in the exact same location as our pressure tongue. Notice how the winds to the west across central Kansas and Oklahoma are out of the northwest, transitioning to much more southwesterly across eastern portions of Kansas and Oklahoma. We also have a very well-defined temperature gradient. Temperatures in the low to mid 60s across central Kansas and Oklahoma, shifting into the mid to upper 70s off to the east. And we have a moisture gradient as well, dew points in the low to mid 50s to the west, 60s off to the east. So we're checking all of our boxes as far as our things to look for go. So it's pretty clear that there is a frontal zone, namely the cold front, situated where these factors are located. So I'm going to draw in our cold front, basically going just south from the surface low center. You see a temperature of 73 here with a south-southwesterly wind, 66 here with a westerly wind. So the cold front goes right through those 2 points, going down through the pressure tongue and right in between where those winds start to shift. Now down here you can see why we can't rely on just temperature alone, even though these fronts are named based on the temperature of the air masses involved. This station here has a temperature of 77 with 79 at that neighboring station right there. So not a big temperature difference at all, but notice the wind shift. Northwesterly winds here shifting immediately to southwesterly there, and a little bit of a moisture gradient developing. 63 dew point at this station, 56 over here. So it's likely the cold front had just passed by this station or was right over the top of this station, and therefore the temperature had not had a chance to respond quite yet. So I'm going to continue through the pressure tongue and go right through those 2 stations. And because the cold air mass to the west is moving into a region of warm air to the east, I'm going to put our triangles on the right side or east side of the cold front boundary. And there we have our cold front. Now let's fill in our warm front. Once again, we see another pressure tongue out here extending off to the east of the surface low, and that is coincident with a wind shift. Winds out of the south across much of central and southern Missouri into Illinois, shifting to much more easterly winds across northern Missouri into Illinois and Iowa. We also have a well-defined temperature gradient as well. Temperatures in the 70s and even 80s down here to the south, 40s and 50s off to the north, and a moisture gradient, dew points in the 60s to the south, 40s and 50s off to the north. So again, all of our boxes are being checked across this region where that pressure tongue and wind shift is, so it's pretty clear that our warm front is located in that region as well. So I'm going to start drawing in our warm front going out to the east from the surface low center. Now notice how in this 1000 millibar isobar the pressure tongue or kink is not really coincident with the wind shift. The pressure tongue is right there. Our wind shift is up in here. Southerly winds at this station, east-northeasterly winds at this station. So the wind shift would be right in here. I tend to side with the wind shift most of all. So I'm going to put the front here just to the north of this station that has the 66 degree surface temperature. So I'm going to go up in here. And then I'm going to bring it down here right through our pressure tongue and our wind shift, which now become pretty much coincident with each other. And because the warm air to the south is moving into a region of cooler air to the north, I'm going to put our semicircles on the north or cool side of the boundary. And there we have our cold front and warm front.
The Chaser Academy is the best deal in storm chasing, and it costs less than a combo meal at McDonald's. Unlock instant access to exclusive storm chasing presentations, participate in live group coaching sessions, and get answers to all of your questions in the unlimited Q&A chat. Whether you're a beginner, a veteran, or somewhere in between, our expert coaches will help you take your storm chasing experience to the next level. Click the join button below this video or on our profile page and enroll in the Chaser Academy right now.
After placing our fronts, we then go and look for any additional boundaries, such as dry lines, outflow boundaries, etc. These, of course, can be vital in storm initiation and intensity. In looking for these boundaries, you want to look for some of the same things that you would for identifying fronts. In the vast majority of cases, these boundaries will be associated with a wind shift, along with a temperature and moisture gradient. They won't always be associated with pressure tongues, but you can look for those as well. But oftentimes, especially for outflow boundaries, you'll see a wind shift coincident with a temperature gradient across a continuous area. And of course, dry lines will often be accompanied by a significant moisture gradient, with hot dry air to the west and warm moist air to the east. In our example here, I don't see any boundaries of note within the warm sector of the cyclone, in other words, between the cold front and the warm front, where that warm moist air mass is situated, so we won't need to worry about that for this case. Aside from these, you can put anything else on your surface map that you might find helpful. One additional thing that is often quite helpful in a severe weather sense is doing an Isodrosotherm analysis, so analyzing moisture. Remember that isodrosotherms are lines of equal dew point, and shading in areas of higher dew points can enlighten where the best low-level moisture is situated. Isodrosotherms are typically outlined in green, and with any of our isopleths aside from isobars, we don't need to worry about them following the wind direction, because these variables are independent of wind. So we're basically just connecting the dots, still keeping in mind that we need to interpolate properly in between data points. In the interest of time, I'm not going to do a full isodrosotherm analysis, but I'll do a couple of isodrosotherms here so you can get the hang of it. We'll start off with our 60 degree Fahrenheit isodrosotherm. Remember, our dew points are these bottom left values in each station plot. So all we're doing is starting at the edge of our domain and kind of working our way across the map. So let's start, say, on the right side of the map here. This is arbitrary, just kind of picking this area to start in. Right away, I see some 56 and 57 points, along with some 66 points over here. So we'll start our 60 line right about in there, right about halfway between those points, maybe just closer to the 50s points, we'll put the line. Now, I do see a 56 and a 64, so we're going to have to go halfway in between those two, and also a 60 dew point exactly at that station right there. So we're going to have to bring our line up to make sure it goes through that station. I see a 56, a 59, and a 65, so we'll be pretty close to that 59 station over there. So I'll keep our line going up just a little bit. See a 59 and a 63, so we'll go just underneath the 59 point. And it's a little hard to see because I put the surface low symbol over the station plot there, so you can't see the dew point, but this dew point right here is 66 degrees. So we have a 66 and a 56, so we'll kind of split the difference there, keeping it a little bit closer to the 56 line. I see a 56 and a 64, so we'll go down in between those two. A 51 and a 64, so we'll go pretty close to the cold front there. 54 and a 55 and a 62 down there, so we'll keep that line fairly close to the cold front. And then a 56 and a 63, so we'll go kind of halfway in between those, just a little bit closer to the 63. And then we'll end our 60 isodrosotherm there, keeping in mind that we need to label this as well. So I'll put a few labels there. And that is how we do an isodrosotherm. Let's now do our 62 degree isodrosotherm. When you're doing an isodrosotherm analysis, or say an isotherm analysis for that matter, using an interval of 2 degrees Fahrenheit is a good practice because, again, that can help you see small-scale fluctuations in the moisture or temperature fields that might be important for severe weather. So our 62 degree isodrosotherm, once again, will start on the right side of the map. We have some 66 points there in our 60 isodrosotherm, so we'll kind of keep it fairly close to the 60 isodrosotherm. We see a 60 and a 64 there, so we'll split the difference right in between those two. 60 and a 65, so we'll keep it fairly close to the 60. 59 and a 63, so we'll bring that one just above that 63 station right there. There's 66 and a 64, so the isodrosotherms are fairly tightly packed in here. We'll bring it back down. There's our 64 point and our 60 line right there, so again, fairly tightly packed in here. There's a 62 point exactly right at that station, so our line will go through that point. And then a 63 right there, so we're going to have to bring it back over between the 60 line and our 63 station, and there we have it. Again, I will label these. A little bit difficult with a lack of space here, but you get the idea. So there's our 62 Isodrosotherm, and we would keep adding those in up to however high you'd need to go for the certain situation. And you might want to start shading Isodrosotherms in, say maybe above 65 degrees or 66 degrees, to really highlight where the best moisture is. But again, this is all kind of up to you, and whatever you think will help you most in your severe weather analysis is going to be what you'll want to include in your map. And we can actually check our work with this one because the folks at the Storm Prediction Center actually did this exact same map and posted it on social media. This is from 19Z on October 24th, 2021, which was a severe weather event that occurred across the Eastern Plains into the Midwest, and it featured several tornadoes. And you can see we did a pretty good job. Our map is on the left, their map is on the right. You can see they have the surface low just like we did in the Kansas City vicinity with the warm front draped off to the east, cold front draped down to the south through the pressure tongue. So comparing our analysis to that of the experts, we did a pretty good job with this one. Now, as you can see, there are some subtle differences, and that's because this is subjective analysis. It's at the discretion of the forecaster, so you're going to get subtle differences from person to person doing the same surface map. But overall, the idea is the same, and our features of note, the surface low, the frontal zones, were placed in very similar locations.
Remember to check out those links in the description below, and then watch another video.